Okay, let's first define diffraction simply. Okay, diffraction is one of the process for waves, and this is simply when a wave passes through a gap, a slit, or sometimes an edge, it diffracts, or you can say it spreads. Okay, this simple process is called diffraction. For example, there was a water wave, and that water wave was passing through a gap, like maybe like this. I'm just drawing the wave fronts. The wave is going this way, and it passes through this gap. There's a gap, right? When it passes through the gap, the wave spreads. Need to be very careful. The wave that we are drawing should have same wavelength as before. Wavelength means, the distance between the two wave fronts. Okay, so should be nearly same. Can you see? Same as before.
Mm.
So this process is simply called as diffraction. If you ask me the reason behind it, so if you see microscopically, suppose, see, I have got some points that I'm marking. Suppose 1, 2, 3, 4, 5. There are 5 points. These points are actually there on the wave front of a wave, and all these points will have to pass through this gap. Now tell me
Okay.
one thing. Suppose number 1, 2, 3, 4, 5. Which of these particles will be having the minimum distance between this wall that I'm showing in green and this wall? What do you think? Minimum distance from these two walls. Which particles while they are passing?
1 and 5.
1 and 5. And they will be very close to the walls, and they will be facing a lot of friction, you can say, a lot of resistance, because they
Mm-hmm.
are very close to the wall, right? And which particle you can say has the maximum distance from both the walls? One particle only.
3.
Three. Exactly. And this particle number three will be facing nearly negligible amount of friction. Okay.
Okay.
As this is quite away from the contact. Okay. So that's the reason
Okay.
why, this particle number three will not be reducing its speed, but particle number 1 and 5 will be reducing their speed to maximum. And particle number 2 and 4 will also be reducing their speed, but less, I mean, they decrease the speed less than particle number 1 and particle number 5. I hope you understand that, right?
Yes.
So this particle or this point, you can say, will be found here because it will be covering the most amount of distance as it has the largest amount of speed through this gap. And particle number 1 will be found here, particle number 5 will be found here, and 2 and 4 will be found maybe here. So can you see this shape will be, formed for this particular wavefront? I hope you understand that, right?
Yes.
Okay, this is the reason why, diffraction takes place in waves. Anyways, I was just discussing with you so you have at least a clear idea that why diffraction takes place. So let's proceed. And this is only a gap. And now I'm going to draw another gap, and another wave is passing through the gap. See, for example, the gap now is quite wide. and the wavelengths are quite short. Okay, now you just imagine I'm not going to draw only 5 particles, but I can draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, even many more, right?
Yes.
That have to pass through the gap. And in this condition, maybe all these particles that are at the center will not be facing any of the friction due to the contact force, and they all will be found here. 1, 2, 3, this way maybe. And this one will be found at the back side, and this one will be found here, and this one will be found here. So eventually, after passing through this gap, the wave will be formed in this way, right? Like that, maybe.
Yes.
Little flatter, you can say, from the center.
Okay.
What do you say? Do you say it more diffraction or less diffraction? More spreading or less spreading?
Less spreading.
Less spreading. Yes, you're right. So less spreading is taking place here. Wavelengths should remain same. I tried very hard to keep them same. There is no change in wavelength during diffraction. Okay, but the spreading is, much less than before. Okay, and
Okay.
next thing is, suppose if the gap is very narrow, I mean, very small gap is there as compared to their wavelengths. So, very small diameter circles will be formed, right? So this is how we understand the diagrams in this way. Okay, so
Okay.
I hope you understand the meaning of diffraction now. And it is not only through the slits or gaps, but it is through the edge as well. For example, you went to a valley and there was a mountain, okay, and you are standing here. Let's say there is a tower that was providing us the telephone signals, I mean, mobile phone signals, and signals were spreading in this way. You are standing here. So due to diffraction only, you will also be getting signals. Okay.
Okay.
Can you see here some spreading of waves taking place, right?
Yes.
Okay. So this is how diffraction takes place. Uh, when a wave passes across or through an edge instead of the gap. There is no gap, but there is an edge, right?
Yes.
Okay, fine, perfect. So we studied diffraction. Now we are coming on to a kind of an equipment that is called diffraction grating. Diffraction grating. And what is diffraction grating? Let me tell you. There is a plain, transparent, thin glass sheet. Okay, and what we do, we take some very sharp object, just like knife or cutter. Okay, and we just make some lines like that. Okay, the lines are many, many in numbers. There are many lines per millimeter. Sometimes 600 lines per millimeter
Okay.
means, you just imagine a millimeter is a very small distance, very short distance, right? And
Yes.
600
Mhm.
lines within 1 millimeter. So you just imagine how many lines are there, or you just imagine the size of this gap between the two lines must be very, very short, right?
Mm.
Okay. So,
Yes.
so this size of the gap behaves like a window for light. Light is incident on this diffraction grating, on this grating, you can say. So, it will be passing through very, very small, narrow slits, right?
Okay.
Okay. And when it passes through the narrow slits, so definitely, as we studied, that when a wave passes through a gap, so it spreads. So the light will also be spreading when it passes through the very narrow gaps, right?
Hmm.
Right. Keeping in mind the condition for diffraction to be observed at its best is you have to keep the size of gap equals to the wavelength. Can you see here? Purposely, I drew the first diagram in this way. See, can you see the wavelength here? And can you see the size of gap? They are equal to each other, right?
Okay.
The size of gap and the wavelength are equal to each other. The diffraction is observed at its best. So you just imagine this size of gap must be nearly equal to nearly, or you may say that it must be close to the wavelength of light. And wavelength of visible light, if you remember, is from 400 nanometers to 700 nanometers.
Hmm.
This is a wavelength of blue light, estimated wavelength. This is the estimated wavelength of red light, and the rest of the colors come in between them, right?
Okay.
Okay, fine. So what I mean, purposely we draw many lines per millimeter, so the window, the gap, the size of slit becomes very, very small, and its size of slit is nearly equal to the wavelength of the light wave, right?
Okay.
Okay, fine. So what we do, we actually place it horizontally, I mean vertically like this. This is actually the grating, and we pass the light through it. Suppose this is the light passing through it, and the angle between the diffraction grating and the light must be 90 degrees. I hope you understand what I mean. I'm showing you the side view. This is the front view, okay? And
Okay, so this
this is the,
vertical line is the distance between the two lines.
no, this vertical line is itself a diffraction grating. Grating.
Okay.
I just turn this grating to 90 degrees and I'm showing you its side view, okay?
Okay.
Yes. And the light is falling on this, diffraction grating, and the light, I'm calling it monochromatic light. Okay. Monochromatic means, light of a single color or wavelength. Okay. Light of a single color
Okay.
or light of a single wavelength is called monochromatic light. Monochromatic light is incident normally means, at 90 degrees on the diffraction grating. Okay.
Okay.
Fine. So, when light passes through this grating, it will spread, means diffraction takes place. Okay. And after diffraction takes place, many light rays will be overlapping each other, will be meeting each other. What is that process called? Overlapping, meeting. What is this
Uh,
process called?
Interference.
Interference or superposition. So, in this diffraction grating process, or in this diffraction grating, or through this diffraction grating, two processes are taking place: diffraction and superposition, both. Superposition and superposition always gives us, as a result, gives us maxima and minima, right?
Yes.
Fine. So what I'm doing, you know, the very first bright light we obtained here, okay, exactly in the direction of the incident light. And that light or that order is called zero order maxima. Okay, this is
Okay.
maxima of zero order. Then, after that, another one may be found here. and found here as well at equal angle like this. Okay. This
Okay.
angle theta1 and this angle theta1 are equal. Sometimes in exam, they give you a question. They say that a student is performing an experiment by using diffraction grating and he found that theta1 is not equal to theta2. What could be the reason behind it? Okay, so there is only one reason behind it. The student may not kept this angle 90 degrees. So the, maxima above the zero order and below the zero order do not have same angle. I hope you understand that.
Okay.
Okay, so if
Mm.
you do not keep this angle 90 degrees, so the pattern will not be symmetric above and below, and the angles like angle 1 and angle 1 above and below will not be same. Okay,
Okay.
anyways, so this order and this order are called first order maxima. Okay,
Okay.
now we find here another maxima and here as well another maxima. This angle from zero order is called theta2. This angle from zero order is also theta2. This is called second order
Yeah.
maxima. Okay, right?
Okay. Yes.
Fine. And in this way, number of maxima can be obtained. Suppose this is going to be third order maximum. Okay, n equals 3 and n equals to 3 here as well. Third order maxima. And the angle theta 3 is this one and this one. I hope you understand that, right?
Yes.
Okay, fine. So number of orders are formed. Purposely, I did not keep this angle and this angle equal to each other. First angle increases by a smaller magnitude. Second angle increases by larger magnitude. Even third, larger than before. And this goes on and on. Understand?
Okay. Yes.
Yes. Anyway, so this is the pattern what we obtained by using diffraction grating. And what we are going to do now, we are going to study a formula that is used to do the calculation. So the formula is very simple. The formula is d sine theta equals n times of lambda. Okay, this n lambda is used only due to maximum. In this case, like diffraction grating, we do not see any minima. We do not consider a minima. We do not have any calculation for minima. We are only working on bright lines, and bright line is a maximum. Okay, so if you remember, this is actually our path difference between the two rays, and path difference becomes and lambda is the condition of maxima, right?
Yes.
So d sine theta equals and lambda is the formula that we will be using for doing the calculation of diffraction grating. Let me first explain what is d, what is theta, and what is n and lambda. D is simply the spacing or one line spacing, you can say. What line spacing? If you remember, this is our D. These are two lines,
Okay.
and the single spacing between the two lines means the width of one slit for light simple is your D. Okay,
Okay.
fine. So one line spacing is D. Theta here is angle of an order from center or from zero order. Okay, and N is the number of order.
Okay.
Number of order means either 1, 2, 3, 4, or so on and so forth. This lambda is the wavelength of monochromatic light. Okay,
Okay.
so this is just the formula. Uh, Most of the times they do not give you D directly. They give you D in this form. There is a diffraction grating having 600 lines per millimeter. They do not give you D directly. They give you D like 600 lines per millimeter. So how we can solve it or how we can do it, simply tell me if there are 600 lines in this much length, 1 millimeter means 1 into 10 exponent minus 3 meters, right?
Mm-hmm.
This is the line spacing. If 600 line spacings are there in 1 into 10 exponent minus 3 meters, so one line spacing will be having how much distance is your D? Simple, go for ratio method. D will be equal to 1 into 10 exponent minus 3 upon 600. What answer comes?
1.67 into 10
Hmm.
minus 6.
Okay. This is the value of D.
Okay.
Means this is the width of one slit only for the light. And that's the reason why the light can diffract when it passes through this small gap. Because this wavelength is short, so the gap should also be very small, right?
Hmm.
Okay, fine. So this is how we find the value of D. Most of the times in the question, they do not give you the value of D directly. Theta is very easy to understand. It is the angle from zero order to the respective order, and is the number of order like 1, 2, 3, 4, 5, 6, and so on and so forth. And lambda is the wavelength. Understand?
Okay. Number of orders will be given. Okay.
Sometimes it is given, the other times they ask you about it. One unknown and the rest known. Okay,
Okay. Okay.
fine. Uh, Let me tell you one more thing. Suppose they ask you to find the number of order, number of maximum order that we obtain by a single diffraction grating. Suppose number of order, what they mean like this, even this and this one as well. How many maximum number of order will be obtained? Suppose if they ask you a question, keeping in mind number of orders can be found by using this formula. Okay, n is found. Okay, and suppose you found the value of n as 2.5. Okay, the answer comes 2.5. And here is a discrete variable. Discrete variable means, if it's complete, then you count it. If it's incomplete, you don't count it. Understand?
Okay. Hmm.
Suppose you have, suppose 60 cents. Okay, and you went to a bakery to buy eggs. He said, okay, each egg is for 25 cents, and you have got 60 cents in your hand, right? You gave 60
Mm-hmm.
cents to him. He will give you two eggs only, and he will return you the change, right?
Yes.
Fine. So he cannot give you the third egg, although you have excess amount of money, but still you will not be getting the third amount of egg because it is just a discrete variable. Egg cannot be halved and give it to you, right? So
Yes.
this is simply called discrete variable. Here as well, you always consider n a discrete variable. Discrete variable means, 2.5 means 2 only. Even 2.9 is 2 only. Okay.
Okay. Okay.
3.92, I mean 3.93, 3.83, 3.1, again 3. Understand?
Yes.
Okay. One more thing is, suppose if they are asking you the number of order to be calculated, okay, and you calculated this 2.5. How you calculated, I'm going to explain it to you. And before I explain you, let me open a past paper question. In the question, it is written a parallel beam of light of wavelength 450 nanometers is incident normally on a diffraction grating, which has 300 lines per millimeter. They said, what is the total number of intensity maxima observed? What they mean, just like in this diagram, they are talking about all of these maxima.
Okay.
Okay. Yes.
Mm.
So how we are going to find it? I'm going to explain it to you by using the formula. See, we are supposed to, first of all, see this as wavelength. This is wavelength, fine, in nanometers. And by using this data, 300 lines per millimeter, we can find out the value of D, right? Because the formula is D sine theta equals n lambda, means n equals D sine theta upon lambda. Okay, so 300 lines are there in this much length, am I right?
Yes.
So we have to find out one line spacing has how much length going this way, and D is
Okay.
going to be 1 into 10 exponent minus 3 upon 300. Okay, and one more thing is, because we are finding how many total maxima are formed, for finding total maxima, the angle taken is this angle. How much angle is this? From zero order to
90.
90 degrees. And we, one by one, we calculate the number of maxima on each side of the zero order. So what we do, because it is symmetric, because the light is incident normally means at 90 degrees. So we will be working on one side only. And later on, we will be double it, okay? Doubling it. Understand?
Okay. Yes.
So what we understand for finding total number of maxima order, we always have to keep theta 90 degrees, right? So I'm doing substitution here. D here is 1 into 10 exponent minus 3 upon 300. This is the value of D. Sine theta means sine 90. That is 1 always upon lambda is 450 into 10 exponent minus 9. Okay. Yes. Do the calculation and tell me the answer for N quickly.
Okay.
Okay. The answer comes 7.4. So first of all, if you remember, I told you this N is a discrete variable. Okay. So
Mm.
what should be my answer?
7.
7 only. Okay. 7 only. So you just imagine, just like this, 7 maxima are there on one side. So definitely 7 will be there on the other side as well, isn't it?
Mm. Yes.
Okay. And in my calculation, this zero order is never included. So one zero order is also present, right?
Okay. Mm.
So how many in total are present?
15.
15. Perfect. So what we need to do, we need to be very, very careful in reading the question, because once you read the question and understand it, then you will be able to answer the question correctly. For example, a parallel beam of light, wavelength this much, incident normally on a diffraction grating. Okay, what is the total number of intensity maxima observed? What they mean, they are asking about all the maxima. Okay.
Okay.
Yes, sometimes they ask you only on one side. Suppose if they ask you calculate the total intensity maxima on one side only, then your answer must be 7 only, right?
Okay. Mm.
And if they ask you all, so 7 above, 7 below, and 1 is at the center, right?
Okay. Mm.
Yes, so finally what we get here is 15 as our answer. I hope you understand that, right?
Yes.
Okay, fine. So this was one of the example question that we solved, but this diffraction grating is not enough, because sometimes they give you the diffraction grating and they tell you that the light that passes through the grating is not a monochromatic light, but it is white light. Okay. And
Okay.
white light is not monochromatic. and it is actually composed of 7 components. Okay, and 7 components, if you remember, if your this side is considered to be blue, okay, and this side is
Mm-hmm.
considered to be red. Okay, so these are the 7 components in white light. So now I'm just writing here white light is incident normally on a diffraction grating. So let's see what kind of pattern we obtain with white light. For example, first of all, the white light goes straight and we get here a white color bright light here. Okay, and that white bright light is simply zero order. Okay,
Okay.
tell me what happens to the white light when it passes through prism.
It spreads into different colors.
Okay, it
There's
splits
7 colors.
into 7 colors, and that spectrum is a continuous spectrum of all 7 colors from violet to red, right?
Yes.
Okay, and the process is called dispersion. Anyways, the same dispersion takes place here as well. Okay, in first order, second order, and so on and so forth. So we do not hear a single maxima here, but we get here a kind of a band like this. This is first order maximum. Okay, and it is definitely there on either sides. Okay, this is first order maxima on like above and below. But we must understand in this first order maxima, there must be 7 components of light present. Okay, you are
Okay.
going to tell me this is A and this is B. Where will you find red and where will you find blue? At A, do you find red or blue? Okay, this is my question, and you can use the formula and can tell me the answer. See, this is the formula d sine theta equals n lambda. And we discussed here that the estimated wavelength of blue is 400 nanometers and the
Okay.
estimated wavelength of red is 700
700.
nanometers. Okay. Now, you know, A has smaller angle than B. Okay. What we can do, we can find out the relationship between angle and lambda. Then we will be able to understand whether A is going to be a blue or red. Okay. Tell me one thing. A
Okay.
has a smaller angle or larger angle than B?
Smaller angle.
Smaller angle. Okay. So this theta and this lambda are directly proportional, are directly related or inversely related?
Uh, Directly related.
Directly related. Okay. So tell me one thing. If they are directly related, which of them, which color of them, like blue or red, have shorter wavelength?
Blue.
Blue has shorter wavelength. So blue should have a smaller angle as well, isn't it?
Yes. Mm.
So
Blue.
A is blue here and B is red here.
Right.
And what about here? CD. Tell me what is C, blue or red?
C is blue.
Okay, C is blue here and D is red here. Absolutely right. So all the rest of the colors are in between. Okay, like this.
Okay.
And then second order maxima is also formed in the same way, maybe like this. Okay, and the second order maxima is even a little broader because of this sine theta. See, theta is not related to lambda directly. Theta has sine as well. So due to the sine theta, the second order is even broader than first order. Even third order is broader than second order, and this goes on and on. And here as well, we get here blue, we get here red, and we get the rest of the colors in between, sandwiched in between, right?
Okay. Mm.
This is blue, this is red, and the rest of the colors are sandwiched in between. Anyway, so this is how we, study the diffraction grating or diffraction of white light through diffraction grating. Okay.
Okay.
Usually there is no such calculation came in past papers, so that's the reason why I'm not telling you the calculation of this only. But sometimes they ask you in MCQs about the diffraction grating or diffraction of white light through diffraction grating. Okay.
Okay.
Okay. Let me tell you the applications of this diffraction grating and the diffraction of light through it. There are two main applications or purposes of this diffraction grating and its use. Purpose number one is going to be the one like at that time there was an argument about electromagnetic radiations. Sometimes scientists used to say that electromagnetic radiations are actually particle nature, or the rest of the particles, rest of the scientists said that they have wave nature. So because diffraction and superposition means interference, both are the properties of wave. So
Mm-hmm.
the diffraction through diffraction grating indicates that light has a wave nature, okay, instead of
Okay.
particle nature. So the first thing about this diffraction and diffraction grating was this one. Second application or second purpose was, the formula d sine theta equals n lambda. This lambda wavelength of light at that time was very difficult to calculate, and this experiment again you know enable us to find out the wavelength of light by using this diffraction grating and diffraction, right?
Okay.
And third thing is, let me tell you an application that you will be studying at higher levels, is spectroscopy. Okay, spectroscopy is a process in which we find out or we identify a gas that is unknown to us. Okay, I mean, if you are given some gas and you do not know what gas is this, so you can go for spectroscopy and can see its spectrum and find out which